how do you detect heteroscedasticity? Did I show you something, a scatter plot where you just saw heteroscedasticity? So the simple way is where you have a regression line and then you look at your scatter plot, and if you see something like this, you notice that the variance is increasing as x is increasing, and this means that you have conditional heteroscedasticity. So the simplest way of detecting whether you have heteroscedasticity or not is to look at a scatter plot. But how do you look at a scatter plot if you have 4 different x variables? Most of us think well in 2 dimensions because all our lives we've studied on 2-dimensional paper. Some smart people can visualize 3 dimensions, but then that's the limit for most of us, right? So a scatter plot won't work if you have more than 1 or 2 x variables. Plus, this is CFA level 2, so we can't have something as simple as a scatter plot and leave it at that. So what we also need to learn is that there is a test called the Bruch-Pagan test. So that's one more thing to remember. So you have a Bruch-Pagan test, and that is your test for heteroscedasticity. But obviously, step 1 is knowing that name, and there are several names based on, like, there'll be Bruch-Pagan, Durbin-Watson, etc., that you need to learn, but we are starting with Bruch-Pagan. So I'm going to help you memorize this. So your test for heteroscedasticity is the Bruch-Pagan test. What is the Bruch-Pagan test? With every test you need a null hypothesis. What's our null hypothesis here? Our null hypothesis is that there is no heteroscedasticity. So what is the alternate? That there is heteroscedasticity. Now, in the Bruch-Pagan test, what you do is you regress the residual with x. What does that mean? Here have we regressed the residual with x. This is your original regression. Then you take out all these residuals and you then regress so the residual becomes the y, and you regress the residual with y. You regress the residual with x. Now, when you regress the residual with x and you look at your statistics, will there be a r squared? Remember, whenever you do a regression, in the third part, one of the things will be the r squared. So there will be the statistics for this original regression. Are you looking at those statistics, or are you looking at the statistics from your second regression, which is a regression of the residual with the x? It's this one that you are looking at. This is the regression of the residuals with the x variable. And then what is the test statistic? The BP test stat. What does BP mean? The Bruch-Pagan. The Bruch-Pagan test stat is computed as the r squared. Which r squared? The r squared from this regression multiplied by n. What do you think n is? N is the number of observations, which also will be the number of residuals. All right. And then how do you decide whether to reject the null or not? You have to compare the test stat with a critical value. And that critical value will be determined from another table that you heard of at level 1 but never really spent time on, which is the chi-squared table. And the degrees of freedom is k over here. So I'm going to pick example 8 from the curriculum that dives into this topic. So I'm skipping the details, but here there is a regression between, or this regression is testing the relationship between interest rates and expected inflation. The question is, why are we using the chi-squared table and not any other table? The point is that in different kinds of tests, you need to use different tables. Like when we were doing the F test, then you need to use the F table. So these are things that, yeah, there's a reason, but I don't know that reason and you don't need to know that reason. We just need to know that this test, this table, and memorize it. Some smart statistician figured all the stuff out. We don't need to understand the derivation. Okay, so in example 8, we are looking at the relationship between interest rates and expected inflation. So you saw this in economics, that there is a relationship between nominal interest rates and expected inflation. So now that you've studied regression, you want to do a regression-based analysis to validate the Fisher effect. I want to make sure you understand the big picture first. When we do a regression, what have we talked about so far up till section 3? What we've talked about so far up till section 3 is we set up the regression equation, then we look at the regression statistics, the ANOVA and so on. We first make sure that the regression is significant overall, then we verify that the coefficients are meaningful. So that's what we did up to the end of section 3. And in this example 8, the first part is doing the regular stuff that we did in section 3, validating that the regression is meaningful and validating that the coefficients B1, B2, etc. In this case, it's just B1, that B1 is statistically significant. But then in section 4, what else do we do? We need to do some additional tests to determine whether the assumptions that need to be made in regression, whether those assumptions hold true or not. And what's the first assumption that we are trying to check? It's the heteroscedasticity versus homoscedasticity assumption. So how do we do this? Actually, what's given over here, in this particular test, before we are testing for heteroscedasticity, in this particular case, they set up a null hypothesis that B1 is equal to 1 versus B1 is not equal to 1. And then there is a whole bunch of work that's done. And these are the regression coefficients. This is before we talk about heteroscedasticity. Does this look significant? The R squared seems generally about 0.5 range is decent. There are 1, 3, 7 observations, but this is a decent number. We are not given the F stat. Let's just assume here that the F stat is decent and we are fine. What do we do next? We need to test for heteroscedasticity. How do we test for heteroscedasticity? By doing the Bruch-Pagan test. And what was the Bruch-Pagan test? You have to regress the residuals with X. Now here is the trick. In the curriculum, right, when they give the data for the original regression, they give you a multiple R squared. Is this the R squared that you use or not? This is not the R squared that you use, because this is the R squared from the original regression between interest rates and inflation. That's not the R squared that you need. And I'll actually read this. The test, this is the Bruch-Pagan test, regresses the squared residuals on the predicted inflation rate. Inflation rate was your X variable, your independent variable. So the R squared in the squared residuals regression, which is not shown here, is 0.1651. So this is the relevant R squared. Now how do you come up with the Bruch-Pagan test stat? It's the 0.1651 multiplied by n. So remember, it is n times the R squared, and this is the R squared of the residual. So what is your test stat? When you multiply n by R squared, you get 22.6. So what is 22.6? Exactly. 22.6 is the Bruch-Pagan test stat. You have to compare this with the test statistic. Then what's the next question? What's the test statistic? And we have already learnt and memorized that the table that we look at is the chi-square table, which that looks like this. At a 5% level of significance, the chi-squared will give us a value of 3.84. So 3.84 is the critical value. So right now just take it as a given that you can read the chi-square table. So given the level of significance and the degrees of freedom, you come up with a critical value of 3.84. Now, Can you reject the null or not? You can reject the null because your test stat is much bigger than the critical value. So that is the point here. Now, does this mean we have heteroscedasticity or we don't? We have. The null hypothesis was no heteroscedasticity, but we have shown that we have heteroscedasticity. So that's how this works. Now, some people get confused because a lot of us have simplistically learnt that the null hypothesis is typically the situation we don't want, and the alternate is what we do want. And here we set up the null hypothesis as what? Yeah, so here we set up the null hypothesis as we saw earlier. The null hypothesis is no heteroscedasticity, and the alternate is there is heteroscedasticity. Now, what you want, what you don't want then becomes a matter of perspective. Here is how I would encourage you to think. Let's say that the regression is being done by your colleague, and what you like to do is poke holes in the work of your colleague, which most people like to do. So your colleague does the regression and shows it to you. So what would you like? You would like to point out that your regression is useless. So you do so he has this wonderful model that explains how you can make a lot of money, but then you point out by doing the Bruce-Pagan test that the model is flawed because it violates your homoscedasticity assumption. In other words, there is a conditional heteroscedasticity problem which you have proven based on the Bruce-Pagan test. So I don't know if that helps or not, but this is how it's supposed to work. All right, so what have we just learned? We have learned what is heteroscedasticity, and we have learned how to detect heteroscedasticity. What's the next thing? How do you correct conditional heteroscedasticity? And why do I say conditional? Because this is the problematic sort of heteroscedasticity. The non-conditional or the other one is not a problem. So we use a method, and here's another term to remember, a method called robust standard errors. And robust simply means that you are making your standard errors better, stronger, more robust. Do you recall what was the issue with heteroscedasticity? The issue was that the standard error was too small, and therefore your B1 minus 0, so your t value became too big. What this method, the robust standard errors method, does is it boosts the standard error. It increases the standard error. If it increases the standard error, then if you start increasing the standard error, that will lower the test stat, which is what you want to do. So it's an adjustment. In most statistical software, there'll be a check button that when you are running regression, you check that button, and then the regression program knows that it needs to use robust standard errors. So then what it will do is it will detect heteroscedasticity, and if it detects heteroscedasticity, it will bump up the standard error, which in turn will bring down the t-stat and make the t-stat more reasonable. So this method increases the standard error, and which lowers the t-stat, making it more accurate. And to show you an example, we were just looking at this inflation and interest rate example, and before we did the correction, if you look at the B1 coefficient, the standard error was 0.08 and the test stat was 10.8. Then in white here, I have taken the standard error with the correction. So when we do the correction, what has happened to the standard error? It's gone from 0.08 up to 0.1. So the standard error has been bumped up. And what does that do to the t-stat? It decreases the t-stat. So this is the better t-stat to look at. Now you've made the correction, you have a better t-stat. Do you think we'll be able to reject the null hypothesis over here? Yeah, we still have a decently high t-stat, but the point is that after adjustment, this 8.6 is the t-stat to look at, not the before adjustment number. That's the main point. The other method is called, the other method for what? For correcting conditional heteroscedasticity is called the generalized least squares method. There is not too much detail on this other than the fact that this method modifies your original equation, your regression equation, in an attempt to eliminate heteroscedasticity. Next problem, serial correlation. This is also called autocorrelation. So here the error terms are correlated across observations. What does this mean? This means that if you have data like this, X and Y, given that you have a lot of seasonality in financial data, you might have a situation like this. Now, what is the error term? These are the error terms. If you have data like this, knowing that this error is positive gives you an indication that the next error will also be positive. And knowing that the error is negative here gives you an indication that most probably the next error is also negative. So if you have one error term, do you have a basis for predicting the next error term? If you have seasonality, you do. That means that there is some correlation between the error terms. If there is correlation between error terms, that again is a violation of one of the assumptions. So what's that violation called? Serial correlation. And what is another term for serial correlation? It is autocorrelation, a correlation between the error terms. So this is a major problem because very often financial data is time series data and there is seasonality. What is the problem that is created by serial correlation? The coefficient estimates are fine, like the B1, B2, these estimates are fine. But again, the standard error is understated, which means that the t-stat is and f-stat are overstated. And they give a false significance. What does this mean? So this means, let's say that your critical value is +2 and -2. When you have serial correlation, that creates the t-stat to be overstated. So let's say that your t-stat should be 1.8, but because of serial correlation, the t-stat becomes 2.4. What will you do? If your t-stat is 2.4, will you reject the null? You will reject the null and you will believe that your data is significant, that B1 is significant. But that will be a false significance because your decision was based on a overstated value of the test stat. The actual value of the test stat should have been 1.8. So in actuality, you should not have been rejecting the null. So that's the problem that's created by serial correlation. So note that both serial correlation and heteroscedasticity create similar issues. How do you detect this? Again, if it's, you can do the scatter plot. So what I did here was a scatter plot. The other is Durbin-Watson statistic. The question is that the curriculum says that the estimates are biased and inconsistent. So the point is that if you have serial correlation, then the t-stat estimates are biased and inconsistent. So I was just giving the direction of the bias. So if you have serial correlation, then your t-stat will be overstated, which is biased. Yeah, the coefficient itself will be fine. But the t-stat that allows you to determine whether the B1 is significant or not, that's the issue. So as I said, the other method is the Durbin-Watson statistic. Now this is the more testable one. Again, to help you remember, there are these, so with heteroscedasticity, who are the two smart guys who you need to remember? Bruce-Pagan. Now the two smart guys are Durbin-Watson. So in all these tests, what are we testing for here? We are testing for serial correlation. There'll be a test statistic. That test statistic will have to be compared with a critical value. Now, for this test, you come up with a test statistic called the DW, or the Durbin-Watson statistic. Here is the ugly formula for the Durbin-Watson statistic that you don't need to memorize. The approximation that is much more useful, and one that you need to memorize, is 2 times 1 minus R, where R is the correlation of residuals from one observation to the next. So this will be something that will be given to you. Now, given this approximation, what is the range of the DW stat? If you have R is equal to 1, there's perfect correlation. What will the DW stat become? If R is 1, then your Durbin-Watson stat will become 0. What if R is equal to minus 1? You have perfect negative correlation. Then your DW stat will become 4. So your range will be from 0 to 4. What is the value of R that you would like? What should be the correlation between the residuals? It should be 0. So if that is indeed the case, then Hasnain, what would the Durbin-Watson stat be if R is 0? 2. So what do you want? So if you want a situation where there is no correlation, then what should the Durbin-Watson stat be? It should be 2. So if you come up with a Durbin-Watson stat of 2, that's a good thing. That is telling you that there is no correlation between the residuals. So value of 2 means no serial correlation. Now going back to example 8, if you look at the data, in the bottom segment of your statistical data, you are given this DW stat of 0.4673. Does this look good, or does it not look good? It looks a little far away from the 2. Remember, you would like to be at 2. It's much lower than 2. Do you think you can use this Durbin-Watson stat to figure out the R? Yeah, so we have this approximate formula, and this is taken straight from the curriculum. You can calculate that R is 0.76. So what is this data telling us? There seems to be serial correlation, but this might be just as in now you need to check whether this is statistically significant or not. So you have your Durbin-Watson stat. What are we going to compare this with? We are going to compare this with a critical value. How do we come up with critical values? Now again, here there's going to be another table that we use. What do you think that table is called? It's called the DW table. All right. Now to look up a critical value in the DW table, you need 3 things. You need the number of observations, K, which is the number of independent variables, and obviously a significance level. Let's say that we have a significance level of 5%, which is our default. In example 8, K is 1. Why is K 1? We just had one independent variable, which was expected inflation. And N is 137. That was the number of observations. What is the critical value? So for this, you need to look up the DW table, which looks something like this. So you will be given the level of significance 5%. That's the default. In our case, we had K equal to 1. That's 1. And you have N. What was N equal to? 137. But this table only goes to 100. So notice we have K is equal to 1. And then we have 2 numbers, DL and DU. So just bear with me for a minute here. And then for 100, we have 1.65 and 1.69. Notice that once you get into the high numbers, this is not changing too much. If you went to 137, you would have a L, this left side is DL or D low, would be a little more than 1.65. And what about DU? This would be also a little more than 1.69. All right, now how do we use this? Can you remember these two numbers, 1.65 and 1.69? What you do is you come to your Durbin-Watson statistic. So what is that table telling us? The table is telling us the critical value. So what are the two numbers we just saw? And 1.69. So this was the DL and the other one was the DU or the D upper, higher, etc. So just bear with me for a minute. What was the range of the whole Durbin-Watson? It was from 0 to 4. And what was the point where we can say that there is no serial correlation? 2. So we are at, our actual stat is 0.47, let's say. From the table, we figured out these two critical values. One critical value was 1.65. The other critical value is 1.69. Now, the way this thing works is if your test stat is in this region, less than 1.65, then you can say with a fair amount of confidence that you reject the hypothesis of no serial correlation. In other words, the data is indicating that there is serial correlation. If you are above 1.69, so you are between 1.69 and 2, then what is the data telling you? That you cannot reject the null hypothesis. What's the null hypothesis? Null hypothesis is no serial correlation. So if your DW statistic is 1.69 or above, at least between 1.69 and 2, and maybe till a little bit above 2, you can say that there is no serial correlation. And what about this region between the DL and DU? This is a can't say region where the evidence is inconclusive. So that's why you have two numbers, because there is a gray area, the inconclusive area. So had the DW stat been 1.67, then you could not say either way. If the DW stat is low, then you can say that there is serial correlation. A low number means high R or small r. Remember, a low DW number, what do I mean by low? What do we mean by low for DW? DW, remember, is between 0 and 4. So low means close to 0. So if DW is closer to 0, so it's 0.4. Does that mean that R is high or low? Actually, that means that, so a low DW number means that R is high. How do I know that? I just showed you, right? So I showed you that a small, so if R is 1, R is high, then that means a low DW number. And if R is negative 1, then you have a high DW number. All right, anyway, coming back to this, I'm saying multiple things to you, so if you are lost now, then you listen to the video again. But what are we trying to do here? We are trying to figure out whether or not to reject the null hypothesis. What was the null hypothesis? Null hypothesis is no serial correlation. So we came up with these two critical values. And then what was our test stat? 0.45. The test stat is below 1.65, so we reject the hypothesis of no serial correlation. So in this data, we do have serial correlation. So the question is negative or positive? So a small number means that we have positive serial correlation. And approximately how much is it? 0.7, which we calculated on the earlier slide. The question is, what if the DW is greater than 2? Then it depends how much greater. So right now we are in this range. So again we use the DL and the DU on the right hand side to figure out whether, so if it is just a little bit above 2, then it is, then there is no serial correlation. If it is much more than 2, closer to 4, then there is correlation, negative correlation. All right. What do you think the next point will be now? How do you correct? And here you use the Hansen method. And this Hansen method is more or less the same thing as the robust standard error. So simplistically, you can think that for both heteroscedasticity and serial correlation, you have the same method. So what do these things do? They adjust your standard errors and recalculate the t statistics. And what's happened over here is, this is in blue is the older one before the correction. So look at what's happening to the standard error here. It's 0.08. And then with the correction, the standard error becomes much higher. And what's happening to the t-stat? It's going from 10.8 down to 5. So the other method is to improve the model specification, explicitly reflect time series, nature of the data, or incorporate the source of correlation. This part is not too testable. In fact, this kind of stuff we cover in the next reading. Right now, what are you learning? That the main method is the robust standard errors method, which essentially adjusts the standard error upwards, which means it reduces the t-stat downwards. The third and final item on this is multi-collinearity. 2 or more x variables are highly correlated with one another. So multi-collinearity means the relationship between the independent variables. That is another violation of one of the regression assumptions. This inflates